Supervised learning stands as a cornerstone of modern machine learning, forming the foundation for countless intelligence systems we interact with daily. Its fundamental purpose is to enable computers to learn from data that has already been labeled with the correct answers. This process allows machines to identify patterns and relationships that human observation might miss. The primary goal of supervised learning is to make accurate predictions or classifications on new, unseen data. Whether it's forecasting future trends or categorizing complex information, these algorithms strive to generalize their learned knowledge. They transform raw data into actionable insights, driving decision-making across various domains. The training process for supervised learning algorithms is meticulously structured. Algorithms are fed datasets where each input example is paired with its corresponding, known correct output or label. This labeled data acts as the teacher, guiding the algorithm's learning journey. During training, the algorithm diligently learns the intricate relationship between the input features and the desired output. It analyzes how different attributes of the data contribute to the final label. This iterative process involves adjusting the algorithm's internal parameters, such as weights and biases, to better capture these underlying patterns. The objective is to minimize the difference between the algorithm's predictions and the actual labels provided in the training data. Through repeated adjustments and evaluations, the model refines its understanding. This optimization ensures that the algorithm becomes increasingly proficient at mapping inputs to their correct outputs. The core principle underpinning supervised learning is generalization. An effective supervised model must not merely memorize the training data but rather learn general rules and patterns. This capability allows it to perform accurately on data it has never encountered before. The true test of a supervised learning model lies in its ability to predict the output for new, unlabeled data with high confidence. If a model only performs well on its training set but fails on new examples, it has not generalized effectively. This generalization is crucial for real-world applicability. Supervised learning is incredibly versatile, making it one of the most widely adopted machine learning paradigms. Its adaptability stems from its ability to tackle a vast array of problems across diverse industries. From simple binary decisions to complex multi-class predictions, its methods are broadly applicable. This broad applicability means that supervised learning algorithms can be tailored to solve specific challenges in almost any field. Their robust framework allows for customization and integration into existing systems. This versatility makes them indispensable tools in the data science toolkit. Supervised learning primarily divides into two main categories, each addressing a distinct type of prediction problem. These categories are regression and classification. Understanding this distinction is fundamental to selecting the appropriate algorithm for a given task. Regression algorithms are employed when the output variable is continuous, meaning it can take any value within a given range. These tasks involve predicting a numerical quantity rather than a discrete category. The goal is to estimate a real-valued output. Classic examples of regression include predicting house prices based on features like size and location, or forecasting daily temperature fluctuations. In these scenarios, the output is a measurable quantity that varies along a spectrum. The algorithm seeks to provide a precise numerical estimate. The aim of regression is to find a function that best fits the relationship between the input features and the continuous output variable. This function acts as a mathematical model that can then be used to make predictions. The better the fit, the more accurate the predictions. Common regression algorithms include linear regression, which models a linear relationship between inputs and output. Polynomial regression extends this to nonlinear relationships, while support vector regression offers robust performance by finding a function that deviates from the actual target by no more than a certain threshold. Classification algorithms, in contrast, are used when the output variable is categorical. This means the algorithm predicts a discrete class label rather than a continuous value. The output belongs to one of several predefined categories. Examples of classification tasks include classifying emails as either spam or not spam, a binary classification problem. Another common application is identifying images, such as distinguishing between cats and dogs, which is also a binary classification. More complex scenarios involve multi-class classification, like categorizing different types of diseases. Common classification algorithms are diverse and powerful. Logistic regression, despite its name, is a classification algorithm that models the probability of a binary outcome. Support vector machines, or SVMs, find an optimal hyperplane to separate data points into different classes. Decision trees make predictions by partitioning the data based on feature values, creating a tree-like structure of decisions. Random forests enhance decision trees by combining multiple trees to improve accuracy and reduce overfitting. K-nearest neighbors, or KNN, classifies new data points based on the majority class of their closest neighbors in the feature space. Evaluating the performance of supervised learning models is a critical step in the machine learning workflow. Performance is assessed using task-relevant metrics, which provide quantitative measures of how well an algorithm is achieving its objective. The choice of metric depends entirely on whether the problem is regression or classification. For regression tasks, specific metrics are used to quantify the difference between predicted and actual continuous values. These metrics help understand the magnitude of prediction errors. They provide insights into the model's accuracy in estimating numerical outcomes. Mean squared error, or MSE, is a widely used regression metric. It calculates the average of the squared differences between predicted and actual values. Squaring the errors penalizes larger errors more heavily, providing a clear indication of overall prediction accuracy. R-squared, also known as the coefficient of determination, is another important regression metric. It represents the proportion of the variance in the dependent variable that is predictable from the independent variables. An R-squared value closer to 1 indicates that the model explains a larger proportion of the variance, suggesting a better fit. For classification tasks, a different set of metrics is employed to evaluate the model's ability to correctly assign class labels. These metrics often consider various aspects of correct and incorrect predictions. They provide a comprehensive view of classification performance. Accuracy is perhaps the most straightforward classification metric, representing the proportion of correctly classified instances out of the total. While intuitive, accuracy can be misleading in cases of imbalanced datasets where one class significantly outnumbers others. Precision measures the proportion of true positive predictions among all positive predictions made by the model. It answers the question, of all instances predicted as positive, how many were actually positive? High precision indicates a low rate of false positives. Recall, also known as sensitivity, measures the proportion of true positive predictions among all actual positive instances. It addresses the question, of all actual positive instances, how many did the model correctly identify? High recall indicates a low rate of false negatives. The F1 score is the harmonic mean of precision and recall, providing a single metric that balances both. It is particularly useful when there is an uneven class distribution, as it penalizes models that perform poorly on either precision or recall. The F1 score offers a more robust evaluation than accuracy alone in many classification scenarios. The choice of algorithm in supervised learning is not arbitrary, it depends on several critical factors. These factors guide practitioners toward the most suitable model for their specific problem. Careful consideration at this stage can significantly impact model performance. The nature of the data is paramount. This includes its type, distribution, size, and the presence of outliers or missing values. Different algorithms are better suited for numerical, categorical, or mixed data types, and some perform better with large datasets than others. The desired output also dictates algorithm selection. Whether the goal is a continuous numerical prediction or a discrete categorical assignment directly determines if a regression or classification algorithm is needed. This fundamental distinction narrows down the choices considerably. Finally, the specific goals of the task play a crucial role. Is interpretability more important than raw predictive power? Are there strict latency requirements for predictions? Understanding these objectives helps in selecting an algorithm that aligns with the practical needs of the application. The supervised learning workflow involves several crucial steps beyond just selecting an algorithm. These steps are essential for building robust and effective models. Neglecting any of them can lead to suboptimal performance or unreliable predictions. Data preprocessing is often the first and most time-consuming step. It involves cleaning the data, handling missing values, removing noise, and transforming features into a suitable format for the algorithm. This foundational work ensures data quality and consistency. Feature engineering is the art and science of creating new input features from existing ones to improve model performance. This might involve combining features, extracting new information, or transforming data to highlight patterns. Effective feature engineering can significantly boost a model's predictive power. Hyperparameter tuning involves optimizing the configuration settings of the chosen algorithm. These hyperparameters are not learned from the data but are set prior to training. Tuning them involves experimenting with different values to find the combination that yields the best performance. The overarching purpose of these workflow steps is to optimize the algorithm's performance. By meticulously preparing the data, enhancing features, and fine-tuning parameters, practitioners can maximize the model's accuracy, efficiency, and generalization capabilities. These steps are iterative and often require domain expertise. Understanding the strengths and weaknesses of different algorithms is essential for building effective models. Each algorithm has its own assumptions, biases, and ideal use cases. Knowing these characteristics helps in making informed decisions and troubleshooting issues. Careful evaluation and validation are equally critical. This involves using appropriate metrics and validation techniques, such as cross-validation, to ensure the model's performance is reliable and generalizes well to unseen data. Rigorous testing prevents deploying models that might fail in real-world scenarios. Supervised learning is not merely a theoretical concept, it is a vital area of research and development that profoundly impacts our world. Its continuous evolution drives innovation across numerous sectors. The advancements in this field are directly linked to progress in artificial intelligence. This paradigm drives advancements in various fields, transforming industries and improving daily life. From enhancing medical diagnostics to personalizing consumer experiences, supervised learning is at the forefront of technological progress. Its influence is pervasive and ever-expanding. The application fields of supervised learning are incredibly diverse and continue to grow. In healthcare, it powers disease diagnosis, drug discovery, and personalized treatment plans. Models can predict patient outcomes or identify anomalies in medical images. In finance, supervised learning algorithms are used for fraud detection, credit scoring, and algorithmic trading. They analyze vast amounts of transactional data to identify suspicious patterns or predict market movements. This helps in managing risk and optimizing investments. Marketing benefits immensely from supervised learning through customer segmentation, recommendation systems, and targeted advertising. Models predict consumer behavior, personalize product suggestions, and optimize campaign strategies. This leads to more effective and efficient marketing efforts. Autonomous systems, such as self-driving cars and robotic automation, rely heavily on supervised learning for perception and decision-making. These systems use models to interpret sensor data, recognize objects, and navigate complex environments. Supervised learning is fundamental to their ability to operate intelligently and safely.